Good morning, everyone. Welcome back. Happy Tuesday. I trust that most of you have seen. I have posted on Blackboard the Exam 2 Solutions video. I mentioned on there in the Exam 2 Solutions video something very important, which is the fact that I have decided to give everyone a 12-point curve on the past exam, the Exam 2. So let's say you got an 88 on the exam. That means you got 100 on the exam. We're about to start, we're about to continue in this lecture, the reactivity and mechanisms lecture, which is chapter 6. And I just wanted to mention before we got started that this chapter 6, is actually kind of short. We had about 30 slides the last lecture. We're going to have about 30 slides today. And I mentioned that only because the next chapter 7, which is about alkyl halides, that's going to be a long one. And so it kind of evens out since we had such a short chapter for 6. Chapter 7 has to be a little long, right? Just to even out the distribution of the information that's being disseminated to you. But anyway, before we continue with chapter 6, I just want to mention something super quick. I was reading this weekend this article about a professor who apparently doesn't correspond much with their students. This one student in their class had, I guess, was passing, doing very well at the very beginning, like an A or a B, and then by this point in the semester, like today, they are getting an F, and they don't know why, and apparently the professor doesn't correspond with their students at all, and they don't do any video lectures or do any office hours or do any virtual classes or anything like that. And so, it's pretty bad for that student. But I was also thinking on the other hand, my students are probably super tired of getting all the correspondence from me, right? Because I'm constantly sending you announcements and emails about things that are due and things that have been posted on Blackboard, videos and stuff. And you see my face every day, multiple times a day, between the lecture videos and the quiz and exam review videos and all that. So, I'm sorry about that. But I just think that that it's important for a professor to communicate with their students, and so. But in any case, I was still thinking to myself, man, my students must get tired of all the times I email them about assignments and tests and due dates and such. Anyway, let's go ahead and get started. Switching the view here so you can see the presentation. Chemical and reactivity, mechanisms continued, right? That's a cont for continued over there under my head. My head's always blocking something on the slide, all right? So, you've heard me mention these two terms multiple times in previous lectures, nucleophiles and electrophiles. So it's time to put a definition to the term, a real definition of the term, right? And we all know that in polar reactions, it involves ions as reactants, as intermediates, and or products, right? And so when you have when you have negative charges, they're attracted to positive charges, right? Which I've said that many times before. But that translates to the fact that electron-rich species, right? Notice there's a color coordination here. Electron-rich species are attracted to electron-deficient species, right? Positive charges are in green here, green-blue, and so is electron-deficient species, right? So there's a color coordination right there to let you see the connection between a negative charge in electron-rich species and a positive charge in electron-deficient species. That goes even further, where this red, or I guess it's maroon, goes on here, where an electron-rich species, right, is a nucleophilic species, whereas an electron-deficient species is an electrophilic species. And in our example, we have a carbon, right? In the electrophilic species example, the carbon is actually methyl chloride, right, where the carbon is connected to a chloride. And we all know that the electronegativity difference between carbon and chloride is immense, right? And so most of the electron density is being pulled away from the carbon, relieving the carbon with a partial positive, as you see here, right? Because the electron density is being pulled towards a more electronegative atom, the chloride. leaving the carbon with the partial positive, and that's why it's electrophilic. It's electron deficient, and it wants some electrons to fill in its gap. It's a hole in its heart, right? Because chloride is taking everything and not giving it back, right? It needs to be a give-give type of relationship, not a give-take chloride, okay? Sharing is caring, Barney says. Anyway, on the other hand, though, we have methyl lithium here. Lithium is connected to the carbon of the methyl, right? So methyl lithium. And lithium is a metal, right? And it's on the other side of the periodic table, quite far from the electronegative side of the periodic table. And so in this case, carbon's actually the more electronegative one, for once, right? And so carbon is actually drawing the electron density down towards it, giving it a partial negative charge, right? And that's why it's a nucleophile. That's why it's a nucleophile. Because it's got electron density with itself, in itself, right? So a phrase you'll hear me say a lot is nucleophilic attack. There we go. Nucleophilic attack. And quite literally what that means is that a nucleophile, something that's electron rich, will attack an electrophile, something that's electron poor, right? In the guise, not the guise, that sounds kind of negative, for the purpose of making a reaction, and because it likes electrons, right? And it's going to form a bond, that kind of thing. So it's a nucleophilic attack. So I'm trying not to, spoiler anything here, because I know that there's going to be the next few slides are going to be going through this pretty detailed. So let me just slow my roll a little bit. I caught myself just before I was about to give away anything for the next slides. Okay, so nucleophiles, they're electron-rich species. They can donate a pair of electrons, and that makes them a Lewis base, which makes sense, right? Because Lewis bases, by definition, are what? Electron pair donors, okay? The more polarizable a nucleophile, the stronger the nucleophile, right? So things that are nucleophiles, like we already said before, methyl lithium, but also ethoxide, because look at that electron richness right there, right? Lone pairs here on the ethanol, right? Also nucleophiles. And then also shared pairs of electrons here from an alkene are also good nucleophiles as well, right? Good nucleophiles as well. On the other hand, we have electrophiles. They are electron deficient species. They can accept a pair of electrons, which makes them Lewis acids, because the definition of a Lewis acid is what? An electron pair acceptor, right? So things like carbocations, right, and partially positive atoms are all electrophilic, right? So here's a partially positive atom, carbon right here, because the chlorine is pulling electron density away, right? And so that's why that is definitely an electrophile there, this carbon here, okay, because it's partially positive. We have here a partially, no, it's not partially, it is a positive carbocation, another good electrophile, right? Another good electrophile. And this is just showing you what it means to have a carbocation, right? It means you have an empty p orbital that is just waiting for an electron, okay, to fill its void, fill its hole in its heart, right? Right. Sadly, though, not any electron will do, right? It just has to be that special electron from that special reactant, okay? So, Skill Builder 6.2, identify the nucleophilic and electrophilic centers on Wiley Plus, right? Wiley Plus can fill that void, maybe, All right, so let's just real quickly, we'll do some examples here of some identifying some nucleophiles and electrophiles, right? There is a table in your textbook, and it's table 6.3. This is part of the table here, right? That gives you a list of common electrophiles and nucleophiles, and I highly recommend you check out that book. You better already have the book, honestly. I highly recommend you check out the chart, okay? So we have things over here like this guy. That's definitely going to be a what? It's going to be a nucleophile because it's got a lone pair there, right? I was about to put an E there. There we go. Nuke. That's a nucleophile. It's got a lone pair there, right? Oh man, this guy over here definitely. That's definitely a nucleophile there. Lots of lone pairs there. Right? Okay. something like this here, carbonyl. Remember that in a carbonyl, most of the electron density is being pulled away from the carbon towards the carbonyl oxygen. Okay, so that means then that this is definitely going to be an electrophile. Okay, same thing is true here. We'll have an electrophile there as well. Right, electrophile there as well. One of you might be asking, how come this guy isn't going to be an electrophile? Well, technically, it is very attracted to lost my train of thought. Oh, the positive. The positive is very attracted to electrons, definitely, right? But the problem, though, is that if you were to have a nucleophile come over here, right? Okay. And try to fill in that bond right there. Right? Now you have oxygen with like 4 bonds. So that's a problem. Right? So it'd be easier if the nucleophile came up here and attacked this carbon, right? And then gave back that electrons to the oxygen, right? And then now you just have a oxygen like this, and then the carbon connected to a nucleophile. Right? So remember, you still have to follow the octet rules too, right? And make sure that you have the right number of valence, right? And oxygen definitely cannot have 4 bonds. It can have 3, but it can't have 4. Okay? All right, so, man, I told you we would get to this point where it's all about pushing arrows, right? And moving electrons around with arrows, okay? Curved arrows are used to show how electrons move as bonds are breaking and forming. Recall their use in acid-base reactions, where we have a base here, and I've drawn this for you so many times. We have a base here with a lone pair and electric charge, right? The electric charge, negative charge. And it comes over here and takes the proton, like so. That makes it so that the bond between the proton and the acid species goes to the acid species, such that the acid species is now the conjugate base, right? And it's got a negative charge, and then the base itself here is now the conjugate acid, right? And it has a proton on it, right? So just a quick review, which is the Lewis acid and which is the Lewis base, okay? Which is the Lewis acid and which is the Lewis base. Well, the electron pair donator here, right, is the base. So that would be the Lewis base, right? And then Lewis acid is the electron pair acceptor. So that's the Lewis acid, right? So you can see that the vast majority of the reactions that we encounter here in organic chemistry are going to be Lewis acid based kind of reactions. You know, it's going to all fall back to our acid base chemistry that we had in the first few chapters. There are 4 main ways that electrons move in a polar reaction: either by nucleophilic attack, which I showed you that earlier very briefly, loss of a leaving group, proton transfer, acid or base, right, or rearrangements. We're going to go through each one of these patterns individually. Now, the first one is a nucleophilic attack. Okay, a nucleophilic attack is a nucleophile attacking an electrophile. So here we have bromine with its plethora of electrons, lone pairs, right, and its negative charge. Okay, and it's the nucleophile, of course, because it wants to give some electrons to the shell of an atom that carbon is right now as a carbocation, right? So the nucleophilic attack happens just like that. The electrons come over from bromine and go towards the carbocation, right? And the resultant here is a bond that's formed between the bromine and the carbon now, because the carbocation is gone, because it's sharing an electron with the bromine that it just got electrons from, right? So again, the electron pair donor is the bromine. Electron pair acceptor here is the electrophile, right? Lewis acid, Lewis base. Or Lewis base is over here, Lewis acid's up here, right? So, just as a reminder, the tail of an arrow starts on the electrons, right? The charge, the negative charge, and the head of the arrow ends on the nucleus or the positive charge, right? So again, this is what I've been telling you before. You've got to be very specific about where those arrows are coming from and where they're going to. Okay, they only flow in one direction, and they have to follow a logical flow. Okay, the electrons end up being shared rather than transferred. So here's another example of a nucleophilic attack, but instead of having just one arrow, like we saw before, it's going to be a two-arrow nucleophilic attack. Here, the nucleophile here is a alcohol connected to something, the nucleophile, and its lone pairs come over and attack what I was mentioning before, how the carbon of a carbonyl is definitely an electrophile, right? Because it's electron deficient. All of its electron density is being drawn towards the oxygen at the top of the carbonyl. So that makes it ripe for attack by a nucleophile. And the nucleophile's electrons come over here and fill in that empty little gap of electron density right there in that carbon. That breaks that bond right there, one of the bonds from the double bond, right? And so the electrons from that bond there go up to the oxygen, leaving you with the oxyanion, but we're going to learn a new term here, a new term for oxyanion here, and it's alkoxide. Right, makes an alkoxide, right? And then the bond there's a bond that has formed between the oxygen of the alcohol and the electrophile, the carbon of the electrophile, right? Alcohol here, nucleophile, attacks the carbon with a partially positive charge because of what? Again, the electron density being drawn away from it by the oxygen at the top of the carbonyl bond, right? So the second arrow can be thought of as a resonance arrow. It basically is a resonance arrow, right? Right? Good stuff. Good stuff. And so you end up with that product right here, which is the same product as that product. So as we go through this, you'll see that I sometimes will combine steps, and so there'll be multiple steps in one line. Excuse me. I've just got all this these alerts on my phone about rain starting, and rain makes me very sleepy. So, stupid rain clouds. You're supposed to be sunny all week long. I want to get on the pool again because I like being in the pool. Anyway, so yes, you'll see me on multiple occasions kind of combine steps, and I'll show you that, in a minute on how we do that kind of thing. So nucleophilic attacks can also happen from pi bonds as well, right? Because pi bonds are electron rich where they're sharing electrons, right? And so here in this example, the pair of electrons being shared between these two carbons are coming up and attacking the sulfur, right? And then the bond between the sulfur and the oxygen go up there, giving you the alkoxide at the top, and then now this what used to be just the benzene is now connected to the sulfur, right? And this is all the way in chapter 18. Wow, you'll learn more about that in chapter 18. Note that only one of the carbon atoms from the pi bond uses the electron pair, the pair of electrons from the pi bond to attack the electrophile, right? All right, so here's pattern 2 for pattern 2 for, I forgot what I called this before. Pattern 2 for polar reactions. So pattern 2 for polar reactions, loss of leaving group, right? And arrow pushing those kinds of reactions. There we go. Loss of leaving group. Heterolytic bond cleavage, an atom or group takes the electron pair, right? So in this case, bromine right here is a good leaving group. And so it can literally just take this pair of electrons in this bond with itself, leaving behind a carbocation, and giving you the bromide ion, right? So that is the loss of the leaving group right here. Loss of the leaving group. Okay? Basically because it left that alkyl bond, right? Or left the carbon. Okay? And so it is common for more than one curved arrow be necessary. It is common for more than one curved arrow be necessary to be shown to show the loss of the leaving group, right? So electron density here. So this statement right here, I got confused because it belongs to that there, and it's a little farther away. And then also my head is blocking the actual example here. So let me move my head out the way. There we go. So in this loss of a leaving group over here, there's only one arrow, right? But sometimes it's necessary to show more than one arrow. Okay, and so here we have a nitrite up top on the top of this benzene here, and its electrons come down from this oxygen right here. That's super electronegative. I mean, sorry, not electronegative, super electron rich, right? Doing resonance, right? And it will form a double bond there. We're not going to draw it yet because there's not enough room to draw the next structure yet. But if it does that, that means that you've got to pop off one of the bonds from the nitrogen, right? Because nitrogen can't have 5 bonds. It can only have 4 or 3 bonds. And so it'll pop off this bond here from this carbon here, flowing down to the cyclohexene ring, the dicyclohexene ring. Not dicyclohexene, the dihexene. The cyclohexane that has 2 double bonds, right? Forming, the double bond right there. And then that makes it so that this bond here has to come off, right? And put a bond there, right? And when it does that, this carbon now needs to lose one of its bond too. This carbon here needs to lose one of its bonds too, right? Otherwise, it will be hypervalent, more than 8 electrons. And so the thing that's going to leave is the good leaving group here, which is the electronegative chlorine right there, right? So you started out with resonance up here, went all the way down here, and then popped off the leaving group right there. Okay? Make sense? Yep. So this leaving group left, and there was only one arrow. But this leaving group down here left over here in the chlorine, and it had 4 arrows. So really, the number of arrows is how many arrows you need is the number of arrows that is necessary for the chlorine or the leaving group to leave in a logical manner, right? Next, let me bring myself back. So the next type of polar reaction that has arrow pushing in it is the proton transfer. That's number 3. That's the next pattern, right? And we've done proton transfers multiple times already in the acid-base reaction, so I don't really need to spend too much time on this slide here, but quite simply, the lone pair over there on that carbonyl oxygen can easily come over here, pull off a proton from H3O, the acid H3O, right? And the electrons between the oxygen and the proton there go to the oxygen, leaving you with a water coming off, right? And then this species here. Okay, that species there. Okay. So the deprotonation of a compound is sometimes shown with a single arrow and a proton in parentheses over the reaction arrow, right? Which I don't like as much, honestly. I like to have the actual full arrow, all the arrows shown. So you could by definition, right? The book says you can do it that way. Let me just show you what's there. Hold on. There we go. Where if you had water coming over here again, right? Basically the reverse reaction of the one up here, right? But water come over here, pull off the proton again from the carbonyl oxygen, right? That's called a deprotonation. And then the bond between the proton and the oxygen, those electrons go back to the oxygen, restoring this positive charge to make it a neutral charge again, giving you this species here, which is the same thing as that species there, right? That's why these are reversible reactions. The arrows are going back and forth there because they're reversible reactions. But you can also draw it the other way here, where you have just the arrow coming down like that, right? Which is just this step here, the last step, right? And then show that in the reversible reaction, a proton is being lost, right? And it would still be correct. But I will tell you now that I definitely prefer it this way more, because that way shows where those electrons came from, where that proton came from, or where that proton went to, right? And that's important to distinguish, to recognize. All right, next. Let me bring myself back. There we go. Proton transfers are distinct. Proton transfers / distinct from resonance, right? So multiple arrows may be necessary to show the complete electron flow when a proton is exchanged, right? So in this case right here, you can see that this hydroxide, and for some reason, there we go. I wasn't drawing for some reason. There we go. The hydroxide's electrons, right, are going to be very basic, and they're going to go over and pull off the proton right here, this proton right there, right, from this aldehyde. Okay. No, not aldehyde. Is that an aldehyde? No, that's not an aldehyde. That is a ketone. Yes, from this ketone. And so what this particular statement is saying here is that you could have the arrow go ahead and come over here, form that double bond there, forcing this double bond to break, going up, making the electrons go up to the oxygen to form the alkoxide, right? All in one step. Or you could have it where the bond here actually just goes there. Okay, and then instead of having it go straight to breaking the double bond and going to the alkoxide, you'd have this species instead, the intermediate species, right, with the carb anion right there, and then this can go do that, go up there, and then come back down again to make the resonance structure, right? Both are correct. Okay, both are correct, and both are what they show right here. Okay. Such electron flow can be thought of as a proton transfer combined with resonance, right? So again, for me though, I definitely prefer this up here, where we do the entire thing, instead of splitting it up into two parts. Right? This is splitting it up in two parts, right? So, but all my quizzes, exams, and assignments are all multiple choice, and so you can do either one, and I won't know as long as you get the answer right. And then we have rearrangements. One of my personal favorite things. It's almost like magic, right? Where carbocations can be stabilized by neighboring groups, right, through slight orbital overlap, and that's called hyperconjugation. So over here we have a methyl group right there, okay, and then we have our carbocation right there. This carbocation has this empty p orbital right here, okay, but if you have some kind of neighboring group like this methyl group right here, right, this methyl group has a p orbital right here, right? This methyl group has a p orbital right there. And it can actually do slight overlap to stabilize, right, this carbocation right here, okay? So the methyl group stabilizes the carbocation by donating some of its electron density into the empty p orbital. Right? So what are the implications of that? Well, what it means then is hyperconjugation can actually help with can actually help with carbocation stability, right? And it brings us to this, right? When you have just a methyl group as a carbocation, it's actually the least stable. But then you get this thing called a primary methyl, where you have at least one substituent, one group, and that's a little bit more stable. A secondary carbocation with two substituents is even more stable than that. And the most stable of them all, of all the carbocations, is a tertiary carbocation when you have three substituents, right? Three groups there, stabilizing the carbocation. Increasing the substitution increases the stability of a carbocation due to the increasing number of adjacent sigma bonds aligned with empty orbitals, right? Empty p orbitals. And I apologize over here. I said this was a p orbital up here from the methyl. That's obviously not a p orbital. That is a sigma bond between a carbon and a hydrogen. So, my bad. You can actually see it right there too. There's like it's an SP right there. It's hard to see, and that's the reason why I said p orbital, but it's hard to see. But there's a little ball right there, right? There's a tiny little ball right there that makes it look like an s orbital. Okay. All right. So what that means then is that we can do rearrangements. Two types of carbocations can rearrange. Two types of carbocation rearrangements happen, right? They're common. We have the hydride shift. And remember what I said before about hydrides. Hydrides are quite literally a hydrogen with two electrons and a negative charge. Okay? And a hydride can easily shift over to a carbocation, just like that. And when it does that, it leaves you with a carbocation on the previous carbon, where the hydride came from. You also have a methide shift. A methide shift is quite literally a methyl group with a lone pair and a negative charge, right? Lone pair with a negative charge. Lone pair with a negative charge on a methyl. There we go. And that can shift as well too, leaving behind the carbocation on the carbon where it came from, and going to a new carbon, right? So the thing about it is that this kind of thing only happens, right, to an adjacent carbon, number one, and then also it can only happen if the resulting carbocation, right, is more stable than the previous carbocation. And you guessed it, right? Dang, it's on the next slide. Put a pin in that. So, multi-step reaction mechanisms are simply a combination of one or more of the four patterns covered thus far. And this is what I was talking about a minute ago, where I combine steps a lot, right? So let's go through this one by one, where a whole bunch of combinations of steps are put together. Okay. We have a bromine here, hydrogen bromide, and the electron pair from the alcohol here takes the bromine takes the proton from the hydrogen bromide, right? Leaving you with a bromine leaving, or a bromide leaving, right? It goes away. And then the resultant product here, right, is a alcohol with a positive charge, right? With a positive charge, because it has an extra proton attached to it. Well, turns out that this water here, this alcohol with an extra proton, looks a lot like water, and water is a good leaving group. And so water can just pop off of the carbon chain, right? And you lose the water, and that's loss of the leaving group, right? Loss of the water. I like to make the arrow the reaction arrow is very exaggerated, so I know exactly what's leaving. And there the water is leaving. Okay. Once the water leaves, it leaves you with a carbocation on the carbon chain, the hydrocarbon, right? And so now you can do a hydrocarbon rearrangement where the methide, right, that's right here, moves over to this carbocation, right? So now it's over here, leaving you with the carbocation now on the carbon that it left from. Then you can do a nucleophilic attack with the bromine that was from over here, right? That's the same bromine. Bromide. It comes over, does a nucleophilic attack on that carbocation there, and you get an ethyl bromide. Fun stuff, right? Did I say ethyl bromide? How many carbons are there? 1, 2, 3, 4. Butane, actually, right? And then 2 methyls, and then 1 bromine, right? And so this would be 2 bromomethyl, and then 3 methyl butane. Okay? Good stuff. Oh, wow. Okay. So often 2 patterns occur in a single mechanism. Now this is what I always do. This is me. I always do this for some reason. Often 2 patterns occur in a single mechanistic step, right? Where you have the nucleophilic attack, right, by the hydroxide. And then you also have the loss of a leaving group, right? And now you've turned this 4 chlorobutane, right, into a 4 butanol, right? And you see here that you have first the nucleophilic attack happen. Well, it happens simultaneously, but when we draw the arrows, it's nucleophilic attack occurs, and then loss of the leaving group. Okay? So, more about arrows, because it's so important that you draw these arrows correctly, where they start. The curved arrow starts on an electron pair, right, or a shared pair in a bond, or a lone pair. Okay? So, on a lone pair, you can see here, electrons are starting and they end on a bond, right? And then the leaving group leaves. Okay? So you can essentially see then that, let me actually erase that and do it so you can see it better. You can see that when the lone pair comes over here and attacks that carbon right there, right? It's going to form a bond between that carbon and the oxygen, but oxygen can only have 4 bonds, right? And if it formed a bond the way it was, don't forget that this also has a hydrogen there and a hydrogen there. It's already got 4 bonds, right? So the question is now, you can see it as 2 different ways here. You can see as chlorine's a good leaving group, so it'll probably leave, right? And then that means then that the oxygen from this this alcohol, right, doing the attack, can then form that bond, right? So the chlorine leaves as a leaving group, and now the oxygen can form a bond, right, between itself and that carbon with no violation of the octet rule because the chlorine has already left as a leaving group, okay, as a chloride. And gives you that structure there, right? Gives you that there. That ether, right? That ether. I think that's diethyl ether. So, the point of the whole thing is that this down here is the same as this here, and here's the electrons moving towards that carbon, right? But nothing from that carbon is leaving, right? So this arrow is incorrect, okay? That arrow is incorrect. It's actually the bond between the carbon and the chlorine that leaves with the chlorine. And that's the leaving group, right? So make sure when you draw these arrows, especially when you see them in multiple choice answers, that you don't have something where an arrow is coming toward one atom, right? And then another arrow is coming from that same atom. Okay, it can't happen that way, right? Can't happen that way. Where the arrows terminate, the head of the arrow shows either the formation of a bond or the formation of a lone pair, right? So in the same example again, over here, like that, we're showing the formation of bond between the oxygen and the carbon, right? And then here, from this bond between the oxygen and chloride, we're showing the formation of a lone pair, because the chlorine leaves as a leaving group, chloride, right? And then you get diethyl ether and the chloride ion, okay? Okay. So this brings me up to this point right here that I skipped ahead in the previous slide, right? You can't just draw an arrow from the oxygen to the carbon, right? Because if you did that, that signifies the formation of a bond, right? And you don't have anything else signifying the formation of a lone pair. In fact, breaking a bond, right? And so since you didn't do that, this violates the octet rule because there's 5 bonds to carbon. You can't do that. Okay? No. Okay? So again, the correct way to do this is to draw the arrow from the oxygen to the carbon, but also simultaneously having the arrow move the bond between the carbon and the chloride, going towards the chloride till it shows that's forming a lone pair, breaking that bond so that carbon doesn't violate the octet rule. Okay? In summary, any curved arrow drawn should describe one of 4 of the patterns discussed thus far, right? So here again, we have a nucleophilic attack. That's one of the patterns. And then we have the loss of a leaving group. That's another pattern, right? That's another pattern. The arrow is unreasonable, right, if it violates the octet rule and doesn't match one of the 4 patterns. So you definitely can't have this double bond right here going all the way over here. Why is it doing that? There's absolutely no reason. Right? Because remember, we have hydrogens there. Right? That carbon's already happy. My head's blocking the way. Let me show you what I put there. There we go. We have hydrogens there. So you draw something like this happening, you're making it look like there's going to be 5 bonds to this carbon. Can't do it. Can't do it. Practice with Skill Builder 6.5 on Wiley+. Your friend and mine, Wiley+. Let me bring myself back. There we go. Let's talk about rearrangements a little further, right? Oh, that's the thing I told you to put a pin in it. Okay. How do you stabilize a carbocation, right? Or what is the more stable carbocation so that you actually have a carbocation rearrangement, okay? When you encounter a carbocation, you must consider if a rearrangement, hydride or methyl shift, or methide shift, right, could result. It really should be methide here because it's not a methyl group moving. It's that CH3 with a lone pair moving, okay? So, should be a methide. Could result in a more stable carbocation, right? So you see a carbocation, but basically it's saying you see a carbocation. Can that carbocation move somewhere else where it would result in a more stable carbocation, right? This is a secondary carbocation. Could it rearrange itself to be a more stable tertiary carbocation? Remember we had that little, I wonder why I jumped so far. I wonder why we waited this long to get to that. But remember we had that slide a few slides back with the methyl group, the primary, the secondary, and the tertiary carbocation. And tertiary carbocations are the most stable, right? Can we rearrange this carbocation somehow so that we have a tertiary one and it's super stable now? Or more stable than it was before? Let's see. Well, identify the protons, identify the hydrogen atoms or the methyl groups on the neighboring carbon atoms, right? On the neighboring carbon atoms. Identify any carbon or methyl attached directly to the neighboring carbon atoms, right? So we have here, these are neighboring carbon atoms, right? As you see, right between is the carbocation. Then we have these atoms, hydrogen atoms here, a methyl group here, and a methyl group here, right? Determine if shifting of one of these groups results in a more stable carbocation, right? So here, maybe, if I shifted this hydrogen, and it's got to move as a hydride, right, over to there, it would leave me, right, like a hydride shift, right, it would leave me with that carbocation. Well, look at that. That's a tertiary carbocation. Look at this. One substitution there, one substitution there, and one substitution there. Not hydrogens, right? That's a tertiary carbocation. I'm already more stable, right? So that's how you know when you'll have a hydride shift or a methide shift, is when moving it results in a more stable carbocation, right? So, in this example, we went straight to moving that proton right there, but you could have moved it anything over around and see which one came out, most stable. The fact, though, that you can move it at all to make it more stable means that, yes, the answer is yes. There will be a rearrangement. Okay? My chair's wheels are stuck. Let me rearrange my chair like I'm rearranging my carbocations. There we go. Okay. Excuse me. Tertiary carbocations typical will not rearrange unless a resonance stabilized carbocation is found, right? So here is an allylic. So what it's saying is that once you have a tertiary carbocation, right, it's not going to rearrange, right, because the secondary and the primary and the non-substituted at all methyl, right, are already less stable than it, okay, than a tertiary carbocation. So a tertiary carbocation will not rearrange unless it can be resonance stabilized, right, when it moves, right. And so here you have an allylic carbocation. Remember allylic carbocations in previous lectures, right? And here we have a carbocation right there. It's already tertiary, which means it's already stable. But if we were to do a hydride shift so that hydrogen atom is there now, it will leave us with the carbocation there, where it left from, like you see there. And since that was right next to a double bond, next door to a double bond, now we can do resonance. Back and forth. Right? So in this case, this tertiary carbocation actually did move, because even more stable than a tertiary carbocation is a resonance stabilized carbocation. Okay? Resonance stabilized carbocation. Okay? Skill Builder 6.6, predicting the carbocation rearrangements. Good luck to you from Wiley Plus. Okay, so reversible and irreversible reaction arrows. So you've seen this already before, where a reversible has two arrows going back and forth, and an irreversible has one arrow just going forward, right? Some reactions are drawn as equilibriums, while others are drawn as irreversible. The question of reversibility is both a kinetic and a thermodynamic one that I actually discussed in the previous lecture, right? Remember I was talking about the thermodynamic product and the kinetic product, right? We got to analyze those graphs and all that stuff. I won't go through that here today. You can just watch that lecture again, if you need a quick review. Right? So, if the attacking nucleophile is a good leaving group, then it will be a reversible attack, right? So in this case, water is our leaving group, right? Water is our nucleophile. And when it attacks that carbocation right there, it forms this guy here, right? It forms that guy right there. But water is actually a really good leaving group, okay? Because water is quite happy on its own. And that's why it's reversible. Okay? And what that means is that when it's reversible, that bond right there can break between the water and the carbocation, or the carbon that used to be the carbocation, leaving behind the tertiary carbocation, which is stable in itself, and the water, right? So, if your nucleophile is a good leaving group, like water, or chlorine, or bromine, or things like that, right? It is reversible. Okay? It is reversible. So what that means then is, spoiler alert, if the nucleophile is a bad leaving group, it's not going to be reversible. Okay? Effectively, it will be irreversible. Oh, crap. I did it again. If the attacking nucleophile is a poor leaving group, it will essentially be irreversible. So here, our nucleophile is a methide, right? A methyl group with an electron pair, right? Negatively charged. And it does an nucleophilic attack on the carbon of the carbonyl, which is, in fact, what? Electron deficient. The electrons from the double bond come up to the oxygen, maybe leaving you the alkoxide, which is right there. And now the methyl group is attached to the used to be the ketone. Turns out, though, methides are bad leaving groups, right? So it's probably going to stay there. Okay? It's probably going to stay there. The reverse reaction does not occur because the methyl group would rather just stay there, right? Then become this methide group. The loss of a leaving group is virtually always reversible, right? So whenever you lose a leaving group, right? Like I said before, bromine is a good leaving group, right? That's always reversible because the bromine can always come back and do the nucleophilic attack again on the carbon, right? Most of the leaving groups encountered act as nucleophiles. Okay? Just like I just did there. So, again, loss of a leaving group is virtually always responsible? Yes, reversible. Okay, now let's talk about proton transfers a little bit. All proton transfers are reversible, right? Like the acid-base kind of reactions, right? But if the pK difference is 10 units or more, it can be considered irreversible. So in this case, right, we have water, with a pKa of 15 or so, right? And this methyl here, this methide again here, comes over as the base, pulls off the proton from water, right? Leaving you with the hydroxide ion. But then we remember, though, that methyl alkane protons, right, their pKas are like in the 50s. Man, that's way more than 10 units than oxygen, than water, right? So you can consider that pretty much irreversible. It's going to stay as the butane, leaving just hydroxide over there on its own, poor guy, right? On the other hand, though, we have butoxide, tert butoxide. It comes over with its lone pair, pulling off a proton, right, as a base from the water. Again, water's pKa is 15, but here, butoxide's pKa, right, tert butoxide pKa is only 18. That's less than 10, so that's going to be a reversible reaction. It can go back and forth, right? Back and forth, becoming tert butoxide and water, and then tert butyl alcohol and hydroxide, right? Back and forth, okay? Remember, 10 units or more. Carbocation rearrangements are generally irreversible, right? Which makes sense because it's only going to happen if going towards that rearrangement is going to be a more stable structure, right? A more stable tertiary carbocation or a more stable resonance stabilized carbocation, right? So thermodynamically, there is no driving force for more stable carbocations to rearrange itself to a less stable one, right? It makes sense. Why would it rearrange itself again? Go backwards. If going forwards to make that tertiary carbocation or making that resonance stabilized carbocation is more stable to begin with, right? Remember, reactions occur based on the fact that something is more stable than the other, and so the reactants want to go towards the more stable structure. And then we have Le Chatelier's principle, right? When considering thermodynamic equilibrium, in addition to comparing relative energies, Le Chatelier's principle must be also considered, right? So here, the product, one of the products of N2 gas, nitrogen gas, right? Oh, sorry, let me say that again. One of the products of this reaction, right, is nitrogen gas, and will escape the reaction mixture, right? And so it becomes impossible for the reaction to be reversible. Does that make sense? So in this reaction here, the lone pair from the nitrogen comes down, right, forms a triple bond there, making it so that the electrons from the nitrogen to the carbon go down to the carbon, giving you this carbon anion right here, right? This carbon anion. But since this reaction also produces nitrogen gas, right, which comes from this here, right? Because literally that bond between the nitrogen and the carbon broke, right? It's nitrogen gas, and it just floats away. It bubbles out of the reaction mixture. And if there's no nitrogen gas there, how can this reaction go backwards, right? It's going to stay as the carb anion, right? Because there's no reactant there for it to go backwards anymore. Okay, so that's Le Chatelier's principle, right? Oh, that's an application of Le Chatelier's principle. Oh, and that ends our lecture on Chapter 6, reactants and reactivity and mechanisms, right? So today, though, you do have some assignments due. You have the chemical reactivity and mechanism assignment due, and you also have quiz 6 due, right? Not due today, I'm sorry. Assigned today. It will be due tomorrow by 7:59 a.m. Also, reminder, exam 3 is on Friday. And then you also have your midterm exam due today by the end of the day, for sure. Because today is Tuesday. Not like yesterday, but today is Tuesday, and your midterm is today. There is no lab assigned today, and the reason why there's no lab assigned today is because your midterm is today, right? And it's due by the end of the day. Do not forget to do your midterm, okay? Do not forget to do your midterm. Thank you very much, and I'll see you tomorrow for the alkyl halide lectures. Good luck on your exam.